Okay, so we will continue with Vito. He will tell us about the operator spectrum in non-relativistic CFTs at large charge.
All right, so thanks a lot for having me today. And I'm actually very excited to talk in front of a real audience, but also for the people on Zoom today. And to start with, I'd like to ask a very... it's going to be complicated if I don't have a slide, I guess. Is that... So even on the computer, it doesn't work. I just have a missing slide. Doesn't matter. But then, okay, I can proceed. Oh no, it's completely random now. It's really weird. I'm sorry.
Okay. Just very unpredictable.
Shall I do it this way? Is it bothering if I just leave full screen?
Okay, I guess you can continue.
Yeah, I'm sorry for that. Okay, yeah, so I wanted to first ask a very, very broad question, namely, what is theory space, right? The set of all the QFTs and the CFTs and the object flows and whatnot, right? And the goal of my talk today will be to give a complete answer to this question. No, it's not. Unfortunately, I only have 15 minutes, so I will restrict my attention to a subsector of it. And in particular, I would add lots of symmetries to my system, right? So that the theory is constrained. And in particular, I will talk about conformal theories. And you already know that the bootstrap, for instance, has been very successful at collecting the CFT data. And there are other regimes in which, for instance, some quantum number takes a very large value, like the arch charge or the spin. And in these regimes, the theory somehow becomes tractable, semi-classically at least. And so arguably, a very natural question is, what happens if I keep adding some more symmetries? And we might expect that if the charge, the corresponding charge, if it takes a very large value, then we might perhaps reach a tractable regime, right? And if such a limit exists, and if there are sensible predictions in this regime, is there a sense in which they are universal? And I will specify in which sense I mean this, right? But if you followed Domenico's talk this morning, you already know the answers, but I will review anyway some of the ingredients. And so I want to take advantage of the framework of effective theories. And in the standard Wilsonian picture, you just write down all possible operators that respect the symmetries. And each of these operators come with a Wilsonian coefficient, right? And this is the price to pay if you use effective descriptions, right? You don't have control, well, you cannot get an explicit expression for the Wilsonian coefficients. However, then the predictions are in some sense universal in the sense that the structure will be universal. However, still, if you want to use effective theories, you have to specify the range of applicability, right? So you have to specify a UV scale and an infrared scale. And the ratio between these two scales gives you an expansion parameter that controls the derivative expansion in the effective action. And so if you compute an observable in the theory in this way, you generally expect to have a power series in epsilon. And if you have, for instance, parity, you would even have an expansion in epsilon squared. Another ingredient that I want to use today is the state operator correspondence. And well, you know what it does, right? It maps the operator spectrum in flat space onto the energy spectrum on the cylinder, right? And the relationship is very simple. So this is a conformal dimension, and R is just the radius of the sphere. So today I will just focus my attention on the conformal dimension, delta Q, of the lowest primary operator of charge Q. And for this, I simply have to compute the corresponding ground state energy on the cylinder. So if you look at the simplest model, right, the O2 model, for instance, the fixed charge sector is mapped onto the superfluid phase for the Goldstone mode associated with the breaking of the symmetry. And there are very two very natural scales that emerge from this analysis, right? One is given by the radius of the sphere, right? And the other one is given by the charge density, because now this is non-vanishing. And if you compute the ratio between these two things, you get some negative power of Q. So if you want epsilon to be very small, you have to require that the charge be very large. And so this is exactly the regime that I want to focus on. And so I also want to give a very intuitive argument on how things scale to leading order. So if I write down the charge density and the energy density in the most naive form, right? I just divide by the volume. I can just look at the limit in which I send the radius of the sphere to infinity, right? The correspondence, the state operator correspondence doesn't tell me which radius I have to pick. So I can just freely send it to infinity if I want. And in order for these two things to stay finite while doing so, I have to satisfy this simple relationship to linear order, right? So we've come to the conclusion that the conformal dimension is an expansion that starts at q to the d plus 1 over d, and then decreases by factors of q to the d over 2 over d, sorry. And people have also considered quantum corrections to this expression. And for, well, people who know what I'm talking about, you might consider computing the spectrum of excitations above the ground state, and then you compute the Casimir energy for these modes, and in the end you get some new expansion that starts at q to the 0. Well, I will not have much time to talk about these today. I will just show you the two examples. This one you saw this morning with Domenico, right? And also the d equals 3. So I'm always in 2 plus 1 and 3 plus 1, right? And there are two senses in which you can consider this thing as universal. First of all, the expansion itself, the form of it, the structure of the expansion is universal, right? The powers that appear here on Q is universal, although these coefficients are unknown, right? And this q to the 0 term here and this log q term here are universal in the sense that they do not appear with a Wilsonian coefficient in front of them, right? So this is a true prediction of the theory. All right, so I'll now try to apply all of this to the non-relativistic case. And for this, I need first to specify what I mean by non-relativistic CFT, right? But you might already know the answer. I will just consider the Schrödinger group, which is simply the Galilean group, right? Centrally extended. And the central extension of the Galilean algebra is a U1 symmetry, and it's associated with the particle number symmetry. So it counts the number of particles in the system. And the other thing is that time under scale transformation scales twice as much as the spatial coordinates. If you think of the Schrödinger equation, you only have one time derivative, but two spatial derivatives. So this is where it comes from. All right. So now I want to implement well, the non-relativistic avatar of the state operator correspondence. And it exists, first of all, which might be surprising, but it works very differently from the one we have in the relativistic case. So in this case, the operator spectrum in flat space, right, is mapped onto the energy spectrum still in flat space, but in the theory that is trapped in a harmonic potential. So this is very different from just moving to the cylinder, right? And the relationship then between the conformal dimension and the energy is simply given by this formula here, and omega is the strength of the potential. And I will just drop some of the constants here from now on. So if you remember your quantum mechanics class, if you have a confining potential, you naturally expect the presence of turning points, right? A region of space where you cannot go classically, right? You only have to consider quantum effects to go beyond that, right? And since I'm in d dimensions, I expect to have a spherical region that is classically defined, right? Where the particles are confined. And this region, I will just call it the cloud or the droplet. And again, I would just try to compute the conformal dimension for the lowest primary. And for this, I need to compute the ground state energy. Again, I have well, a Goldstone mode, right, that is associated with the breaking of my charge. And the fixed charge sector is mapped again on the superfluid phase for this Goldstone mode in trap. And so what are the skills that define my problem here? Again, I have a, well, physically extended object that is a cloud, right? So its radius sets an infrared scale. And the UV scale is again given by the charge density. However, in my case, it's the ground state is inhomogeneous, right? It's harder for the particles to reach the boundary of my cloud because there is a potential, right? So the charge density is actually non-constant. But I might just take it in the center or in the region that we call the bulk, which means that I'm not going too close to the boundary. And so in this case, it scales like this. And so my expansion parameter in this case is just given by, again, a negative power of Q, and the large charge regime is well defined again. So I can repeat the same game as before, namely I write down the charge density and the energy density, and I collect all the appropriate factors. And in particular, I want to collect the factors of omega, which characterizes the strength of the potential. And this parameter is free. I can choose it the way I want, right? Exactly as the radius of the sphere before. So if I decide to send this thing to 0 while keeping these two objects finite, I have again to satisfy this relationship here. So it seems like we've reached this conclusion, which is exactly the same as before, namely that the conformal dimension is an expansion that starts at d plus 1 over d, and then is suppressed by the same factor as before. So it might be surprising that it works exactly the same in the non-relativistic case as in the relativistic case, but it's also a bit disappointing, right? However, you might have already spotted the missing part of the story, which is about the boundary, right? Now I'm considering a system that has a boundary, and it is associated with the vanishing of the charge density, right? When there is no more particles, there is no more system, right? And so my system has sort of a Dirichlet boundary condition on which the charge density vanishes completely, right? And I cannot resolve details that are too close to the boundary with my EFT because it is not defined for too small details. However, I can play the same game as I would do with boundary CFTs, namely I can place operators that live on the boundary of my system, and impose some consistency conditions in such a way that they are compatible with my bulk theory. And then I can play the same game as before, namely try to identify the expansion parameter and how the leading order contribution to the conformal dimension go. And so what I will find is that the expansion parameter goes like the cubic root of the one that I had before. So it's a much more refined expansion coming from the edge, from the boundary, right? And these contributions start at this power of Q. So I will come to the conclusion and show you the final result. But as you might expect, right, there are certain details that I could not present in this very simple line of argument because I tried not to show any effective action today, although all of this relies upon effective actions. So this was a very, I guess, simple argument, but the full answer is as follows, right? So I hope I managed to convince you that these two lines are indeed present. So the first one comes from a full bulk analysis, right? The second one comes from the boundary story that I've just told you about, right? And this is some sort of, I guess, accidental structure, but it comes really from the edge again. And if you want some explicit examples, I showed here the 2 plus 1 and the 3 plus 1 examples here, which are much richer and much more refined than the relativistic case. So I guess this is very interesting per se. There are certain things that I could not tell you about today. And there, in particular, there is a very beautiful interplay between the boundary theory and the bulk theory in the sense that the boundary operators are actually used as counterterms for some of the divergences that come from the bulk theory. And this yields some logarithms like this one here, right? Or this one here. And generally speaking, they hide into the B coefficients here sometimes. It's actually very subtle the way they appear. I also didn't have the time to tell you about the computation of the Casimir energy that gives these universal predictions here to the that scale like q to the 0 and log q here. And also, I'd like you to take a moment to think about what we've been talking about today, namely a gas of particle trapped in a harmonic potential. And this might ring a bell if you are reading the experimental literature, because people have been doing that in the lab for at least 40 years, right? So the non-relativistic state operator correspondence is an accidental exact mapping between theory and experiment, which I think is absolutely amazing. And so we are actually computing the energy spectrum of the unitary Fermi gas without even knowing it. So I think it's very remarkable. And I'll let you with my outlook slide without commenting it. So thanks a lot for the attention.
Questions? Well,
sorry, yeah.
So did you explore the fact the edge of the cloud on other observables? They have on states or correction functions?
Okay, so we haven't tried to compute the correlation functions yet. Although Kravek and Pal did some work in this direction 3 years ago or so. So for sure, the boundary effects only enter to subleading order, right? So we haven't tried to resolve that far the expansion, the OP coefficients.
Regarding this point that you mentioned, the comparison with experiments, so is there data on that?
Yes, exactly. So yes, the answer is yes. So there are some observables like they've been measuring the linear profile, the way they say it, but it's just like the density, the radial density of the cloud, for instance. And this is a function of the charge, for instance. And I don't think that the resolution of the experimental data is good enough to care about subleading corrections yet. Also, the particle number is huge in these experiments. It's like 10 to the 4, 10 to the 5, right? So if we could resolve, if we could do the experiments for smaller values of the charge, then for sure we would perhaps.
But the leading terms, they match your.
Yeah, sure. So the leading term is the Thomas Fermi approximation. This is well known and it matches exactly.